Hello guys, so in this video we're going to find out how to compute the gradient of a multivariable function along a point. So in this case, what's highlighted in the red rectangle is the multivariable function that we're going to look for that we're given. So in this case it's x squared plus y squared inside a square root, evaluated at the gradient along the point P, which is -2, +3. And the formula that we're going to use is what's highlighted in the blue rectangle, which is partial x squared plus partial y squared inside a square root. So this value will be a scalar value, not a vector. So our gradient will be a magnitude, because gradient is a magnitude, and it gives us the shortest distance between the shortest distance of a multivariable function from the origin. Anyways, without further ado, step one. What we're going to do in step one is we're simply just going to find the partial derivatives of x and y. So notice that this function, x squared plus y squared inside a square root, is a function within the function. So we're going to actually apply the chain rule. So in doing so, I'm going to go ahead and do a dashed line to separate fy as well as f of x, or partial x and partial y. So I'm going to set up my f is equal to u square root, which is equal to u to the 1/2. Our g is equal to u, the inside function. And this is just me applying the chain rule from Cal 1. If you're not confident on how to apply chain rule, I have a video on that in my Cal 1 playlist, not on my Cal 3 playlist. I do have a separate video for chain rule for partial derivatives, which is the Cal 3 version. But anyways, so all I'm simply doing here is just identifying my f, g, and my g is the inside function. F prime would be the derivative of 1/2, which is 1/2 u times u to the 1/2 in the denominator. And then g prime is the derivative of the inside function. With respect to x, the derivative of x squared plus y squared is a constant, but x squared is not, so it would be 2x. So now that we have our partial derivatives, what we're going to do is we're going to apply the chain rule. So what is the chain rule? I mean, we already applied it, but basically when we're taking the derivative applying the chain rule, we multiply f prime times g prime, and that's all to it. Nothing else. Nothing more complicated than that. F prime times g prime. And again, I have Cal 1 video on that. So now anyways, so when we do f prime times g prime, because that's the chain rule, we get 1/2 our f prime, which is 1/2 u times u to the 1/2 in the denominator, times g prime, which is 2x. And then we're going to cancel the 2's out, and then what are we left with? Our partial x is equal to, let me scroll down a bit, x divided by x squared plus y squared to the 1/2. And now that we have it, we're going to rewrite it in radical form. So x, and they're all the same thing. I mean, if you're in Cal 3, you should understand that it's the same thing. 1/2 in the radical. 1/2 power is equal to radical. Alright, so that's x squared plus y squared. So that's our partial x. What about partial y? So I'm going to draw a line to separate those. Partial y, we're doing the exact same thing. So our function was x squared plus y squared inside a square root. So our f will be the radical of u. U is the inside function, or f is the outside function, sorry. U is the inside function, so our g is equal to whatever's on the inside, which is our u. And this would be x squared plus y squared. F prime would be the derivative of u to the 1/2. And the reason I rewrite it as u to the 1/2 is because it's easier to take the derivative of it than if it was not in the form of u to the 1/2. So the derivative of u to the 1/2 is 1/2 times u to the negative 1/2, which you can rewrite as 1/2 times u to the positive 1/2, as long as you keep it in the denominator. And the derivative of the inside function g prime, with respect to y, because this is the partial y now, it's not partial x. Our x squared is a constant, so the derivative of a constant is 0. Our y squared, however, the derivative with respect to y would be 2y. So now we're going to do the same thing. We're going to apply the chain rule. And in doing so, we know the chain rule is f prime times g prime, which is equal to 2 times u to the 1/2. Furthermore, times the derivative of g prime. What's our g prime? 2y. And then we see that the 2's cancel out. So now we're left with the partial of y is equal to y divided by x squared plus y squared to the 1/2. And now we can rewrite this 1/2 as a radical. So this radical is equal to y divided by x squared plus y squared inside a square root. And this is our radical, this is our partial y. So now that we have that, we can move on to step 2. So now that we have the partial x and we have the partial y evaluated in step 1, we found the partial derivatives of the function x squared plus y squared. The next step in step 2 is I'm going to keep brackets around the partial x and partial y that we found. In step 2, we're going to evaluate partial x and partial y at the point of xy. So what was our point? Well, our point is, I'll go ahead and make note of it. Our point is -2, +3. Where am I getting this from? This was actually given to us in the problem. And whenever you're finding a gradient along a point, you have to be given the point. At least for the purposes of Cal 3. You'll always be given either a point or a vector, but when it comes with respect to gradient, it's always going to be a point. So now we're going to use this point that I got from -2, 3. And then all we're simply doing is evaluating partial x and partial y at this point. So partial x evaluated at -2, +3 is equal to, partial x was equal to x divided by x squared plus y squared. And all we're simply doing is literally just plugging in -2 for x and +3 for y, wherever we see it in the partial x, partial y. So -2 squared plus 3 squared, and then we get this, so we get -2 divided by the square root of 13. So that's our partial x. So I'm going to put orange brackets around it because we're going to come back to it. The same way I did, I put red brackets around the partial x and partial y. So now partial y, as we can see right there, partial y is y evaluated at -2, +3 is equal to y divided by x squared plus y squared inside the root. So in doing so, when we plug this number in, when we plug in x and y, we get 3 divided by -2 squared plus 3 squared inside a square root. Then when plugging in this number, we get +3 over the square root of 13. So now that's how we find partial x and partial y at a point P. All we're literally doing is just plugging in numbers. And this is equal to f of x, or partial x, evaluated at x, y, and then +3 over root 13 is equal to partial y evaluated at x, y. So now that we've completed steps 1 and 2, step 1 we found the partial derivatives, and step 2 we evaluated them at the point P. For step 3, what we're going to do is we're going to plug them into the formula and solve for the gradient. So what is the formula? Well, the formula, if you recall it, I had it at the beginning of this problem. And I'll zoom in real quick so you can see what formula it is that we're going to use. So we're asked to find the gradient along the point. So do we see the gradient f is equal to partial x squared plus partial y squared inside a square root? Why? Well, this is because gradient is a magnitude. So we're going to go ahead and use that formula. So gradient will find the shortest distance between two directional derivatives, but basically we're just asked to we're asked to find the gradient along the point. So we have the values of partial x and partial y evaluated at the point P. Now what we're going to do is we're simply just going to plug it into the formula. So the formula, I'll rewrite it here so we can reference it. So this is the formula we're going to use. Partial x squared plus partial y squared. In doing so, we plug in the points, we plug in the values that we got in step 2, which we got -2/13. So that would be our partial x squared. And then we do the same thing for partial y. We plug in the values that we got for partial y, which was +3/13 square rooted. And now furthermore, all we do is just simply solve. So now that we have the values, we're simply just going to solve for the delta f. So in doing so, when we square these, squaring -2, we get +4. Squaring the square root of 13, we get 13. And then, since they have the same denominator, we can add them, which is what we're going to go ahead and do over here. So we get 13/13 square rooted. And then in doing so, 13/13 is 1. So that is our answer. So we say that the gradient equals 1 at the point of -2x, +3y. Thank you for watching. I hope that was helpful. So in this example, we're going to compute the gradient along a point, and we're given the multivariable function inside the red rectangle, which is y⁴/3 plus x⁵ times z plus z times y³. That is our multivariable function along the point +1x, +4y, 0z. And here we're going to formula for gradient. Unlike the previous example, it's basically fx squared plus fy squared plus fz squared. That's supposed to be a z, not a 2, so just pretend that's a z for now. Anyways, it's the same thing, except now we have 3 variables because we have a z, which we didn't have in the previous example. So now, for step 1, we compute the partial derivatives of fx, fy, and fz. So the partial derivative of partial derivative of x is equal to y⁴/3 is a constant, z times y³ is a constant. Why? Because there's no x term. However, the middle term x⁵ times z is not a constant, only the z, but the x⁵ is what we derive with respect to. And in doing so, we get 5x⁴ times z. So that's our partial x. Now our partial y, the middle term x⁵ times z has no y term, so that's a constant that goes to 0. However, y⁴/3 has a y term, z times y³ has a y term, so now the partial derivative with respect to y. So for the first term, y⁴/3, we get 4y³, which is just the y⁴ over 3. 3, the 1/3 is just a constant, so we technically just derived y⁴ power, which is 4y³, plus z times y³ plus z is a constant, so we leave it, and then the y³, taking the derivative of y³ would be 3y² times z. So that's our partial with respect to y. So 3y² times z. Now the partial derivative with respect to z, we have 2 z functions. We have the first one, y⁴ divided by 3, that one goes to 0. However, the next one is x⁵ times z. The x⁵ is treated as a constant, so we're just deriving with respect to z. So the derivative of z with respect to z would just be 1. So it's just times x⁵ plus z times y³. The derivative of z with respect to z is 1, so we're left with y³, the constant. And now I'm going to color code these. Orange brackets for f of x, for partial x, yellow brackets for partial y, pink brackets for partial z. So that's step 1. Now on to step 2. So now that we completed step 1, which was just simply to find the partial derivatives of the function that we were given, which was, as we can see here in the red rectangle, y⁴ divided by 3 plus x to the 5th power times z plus z times y cubed. We found the partial derivatives for step 1. So in step 2, we're going to evaluate these partial derivatives at the point p, x, y, z. What's our point? Well, our point is plus 1, plus 4, 0. So what I'm going to do is I'm going to make note of the point so I don't have to scroll back upwards. And we get these values. So all we're literally going to do now is just plug it in. So partial x, it was equal to 5x to the 4th power times z. And we plug in, and here let me rewrite this, partial x evaluated at these points would give us 5x to the 4th times z, and this is equal to 5 times plus 1 to the 4th power times 0, because z, we plug in 0 for z. And well, what we know will happen is we know that all this will 0 out because of the 0, so our partial x evaluated will actually just be 0. So now on to partial y, evaluated at plus 1, plus 4, plus 0. And, well, I'm going to make room, so I'm going to scroll down a little bit further. So our partial y, evaluated at plus 1, plus 4, 0, will be equal to 4y cubed over 3 plus 3y squared times z. And this is just the partial derivative with respect to y that I computed in step 1. And now we're going to plug in the points. So 4 times y, our y is plus 4, positive 4 cubed over 3 plus our 3y squared plus z would be 3 times positive 4 squared times z. What's our z is 0. So we know all that term zeroes out. So the only term that will be taken into account will be the first term. So it's 4 cubed times 4 over 3. We know 4 cubed is 64. 64 times 4 is 256 divided by 3. We can leave it as a fraction for now. And this is our partial y evaluated. What about partial z? So our partial z, as we can see right here, is x to the 5th plus y cubed. Partial z is inside those pink brackets. So now partial z is equal to partial z evaluated at plus 1, plus 4, 0. Partial z was x to the 5th plus y cubed. And when we evaluate partial z, we get plus 1 to the 5th power plus 4 cubed. Positive 4 cubed is 64, because 4 times 4 is 16. 16 times 4 is 64. Plus 1 to the 5th power, 1 to the infinity power, 1 to any power is simply going to be 1. So 1 plus 64 is equal to 65. And that's our partial z evaluated. So now on to step. So now that we have computed the partial derivatives at the x, y, and z for step 3, what we're going to do is we're going to plug them into the gradient formula and solve for the gradient. So in this case, what's the formula? Well, if you recall from the beginning of the problem, we're asked to find the gradient along the point plus 1x plus 4y 0z. So keep in mind that the gradient formula is what's highlighted inside the blue rectangle, which would be partial x squared plus partial y squared plus partial z squared. Since we already evaluated, partial x is a scalar, partial y is a scalar, and partial z is a scalar. So now what we're going to do is simply just plug it in the formula. So right here I'm going to rewrite the formula. The gradient along a point would be partial x squared plus partial y squared plus partial z squared inside a square root, because gradient is a magnitude. So now all we're literally going to do is just plug in the points. So what is our partial x? Our partial x was evaluated to be 0. So I'll go ahead and circle it. Our partial x was evaluated to be 0 squared plus our partial y. Which one was our partial y? our partial y was evaluated to be 256 over 3. So 256 over 3 squared plus our partial z, which we can see was evaluated to be 65. So it's plus 65 squared. And from here, it's just a matter of literally just plugging it in your calculator. And when we plugged in the calculator, or at least when I did, when you're supposed to get 107.27 as the gradient along the point. So that's how you compute gradient. So the gradient is 3 easy steps. So in quick retrospect, I'm going to go over what I just did for this whole entire problem in like 30 seconds. So in step 1, the first thing we do is we find the partial derivatives of the multivariable function that was given to us, which was this one, y to the 4th divided by 3 plus x to the 5th times z plus z times y cubed. The first thing we did was find the partial x, partial y, partial z. Now the partial derivative of this one was very simple because it was just, there was no special derivatives that we had to use. We just simply used the power rule for derivatives. Step 2, we evaluated by plugging in x, y, point x, y, and z for partial x, partial y, and partial z. We got the values 0, 256 over 3, and 65. And in step 3, all we literally did was just plug it into the formula for gradient. Thank you for watching.